the early technology cinema again. So, having given an applications talk this morning, sorry, you have to put up with me again this afternoon. Apparently there was a reshuffle to accommodate somebody, but this is the implementation talk. So, this morning I was talking about borrowing from a mathematical idea of a polytope. This afternoon I'm talking about borrowing from something somewhere else you might never have reached. So I'll try a quick test. If I say to you, chips, if you think about fried potatoes, then you failed the test. You need to be thinking about things like FPGAs. So the title of this talk is The Reduceron. Nice name, I didn't make it up. It was made up by Naylor, who's one of my PhD students, and this is very much his work that I'm describing. He's actually giving another paper at another conference simultaneously, which is tricky. And titled Widening the von Neumann Bottleneck, which I'm sure you've all read about, having read from childhood, very nice 78 Backus paper. We talked about the von Neumann Bottleneck for graph reduction using an FPGA. Now, bearing in mind what I've just said, your first question just might remind me, what is an FPGA? Well, an FPGA, and in particular, the kind of field programmable gate array that is being used in this work is one made by Zolix. It's not, I should point out, even at this early stage, it's not a particularly new FPGA. It's a few years old now. For those who care about such things, it's a Vertex 2. Well, okay, but what is an FPGA? Well, let me contrast with what you usually compute on, which is probably, well, might be a PC or a nicer machine made by Apple or something like that. Well, that has one memory, hence the possibility of a bottleneck in all the processing trying to do serial transactions with that one memory. So the first thing to notice about an FPGA is that, well, in this particular type of FPGA, you actually have 56 memories, each of which is a dual port, so you can read and write, or indeed do a double read or whatever, block RAM. And each memory, notice, is pretty small. It's 1K by 18 bits. So I already like this. It's sounding sort of minimalist. Okay, what about the processing? Where is the CPU? There is no CPU. That would be monstrously complicated. Instead, we have a very large number of little things called slices, which are the way in which we express the processing we want to occur. And slices are made up out of a couple of configurable logic blocks, and their results can be combined using multiplexers, which are provided. These are 1-bit multiplexers, and a configurable logic block has a lookup table where we can encode functions of 4 bits to give a bit. We have some local memory, namely 1 bit of local memory. So you get the idea? So we've got all this stuff, but it's very light, it's very small. Loads of memories, loads of slices, but no big clunky CPU, nothing frozen in. Highly configurable. We can wire, notice I've not shown these things connected up, because we can actually configure, we can program this programmable gate array in pretty much any way we want. And the principle, if you remember your hardware education, such as it goes, mine wasn't very extensive, I have to admit, the idea is you build large components from small ones, whatever you want. You've got small RAMs, if you want a bigger RAM, you cascade small RAMs. If you want the register, well, you better cascade some 1-bit flip-flops. Okay, well, if that's what an FPGA is, why would we want to do graph reduction on an FPGA? Well, to cut to the bottom line, here's a funny piece of hardware that might do something useful. Suppose you had one of these on a card, and you could plug it into your PC, and it was the functional programs go faster card. You might be pleased. So that's one way of motivating it. But a little more specifically than that, apart from that sort of wish in the sky, is there some more particular reason to suppose that that wish might ever come true? Well, graph reduction is a memory-intensive process. We heard mention of this a little this morning, where, okay, it's a rather extreme example, but we had mentioned a big difference in performance between an imperative computation and a computational one, a functional programming one by graph reduction, and it's because of this very intensive turning over of memory. But very particularly, it's not just general heap allocation, but the whole process of beta reduction, however that is encoded, is in some form or other building the body of a function, in order that that in turn will be reduced if we implement graph reduction. And that process of graph reduction would usually be compiled to many consecutive instructions. And there are no, or almost no, data dependencies between them. So this essential operation, even before we get to parallel reduction, in the sense of many reductions going on at once in our functional program, if we just look at what is involved in computing a single reduction, there's an awful lot of missed opportunity for parallel computation if we are on a serial processor with a single memory. FPGAs have many independent memories which can be accessed in parallel. So the motivating idea is to head towards graph reduction on the FPGA. Okay. What kind of graph reduction? Shall we take the very latest abstract machine? Well, that might be complex, and this is a first push in this direction, so let's rather take a very simple model of graph reduction, usually referred to as template instantiation. So this is the idea when you do lambda lifting, essentially your programs are now, all parameters are explicit at the top level, so we can think of function bodies as like templates. And when we do a reduce a function application, we make a copy of its body, and of course we install references to the actual arguments in place of argument variables. And as Simon P.J. has said in print, this is the simplest possible implementation of a functional language. I'm not sure he meant it entirely positively, but on the other hand, it has its positive aspect. The nice thing about template instantiation from our point of view is that we see an immediate opportunity for parallel memory use. Why is that? Well, think what's happening. We are copying from template memory, whatever that is, to heap memory, whatever that is, at the same time as substituting from stack memory, whatever that is. Now on your PC, on your desk, those memories will all have to be one and the same. And accesses to that memory would have to take their turn serially to shout down the tube that is the unknown copy. But if each of those memories was separate, small regions of memory that could be accessed in parallel, we can do all those things in one clock cycle. What about the interpretive overhead of template instantiation, for which it is notorious? Well, what about the interpretive overhead of an Intel PC? And if you looked inside there to see what it's doing, down on FPGA, there's no reason to be any more scared of interpretive overhead than in a PC design. I'm no fan of software treacle. I don't like swimming at the bottom of a deep ocean of software treacle above me, and I'm no fan of hardware treacle either. So interpretive overhead is not so much an issue as you might expect. Okay, so having, I hope, motivated what we want to do and why we want to do it, what I'm going to do in the next few slides is to say, okay, take your functional program in imagination. Let's suppose it's written in Haskell, which is what I was written in, but I don't think there's anything terribly Haskell specific here. How are we going to compile this thing for Well, we know we're going to compile it for some form of template instantiation, but template instantiation suited for a very simple FPGA appropriate implementation. Well, the start of the story is pretty much standard. Neil made mention this morning of YHC, your Haskell compiler. It's a little bit of a, it is a bytecode compiler. Fairly quick bytecode compiler, and like almost all compilers you've ever seen for a functional language, begins by doing the front-endy sort of stuff, and it reduces the program to some kind of core, smaller language. So, stuff is lambda lifted, we extract supercombinator definitions, applications are arity saturated, so we don't have to worry about that kind of thing. So, for example, take this as a little running example, factorial. Will, after that process, look something like that. Nothing surprising, completely standard. In the next stage, and at this point I'm very pleased to put right an omission, although it is a draft paper, nevertheless it was an omission in the draft that you have, not to cite the SAPL interpreter that we heard mention of this morning. Don't know whether the SAPL people are here. Are you here? Does anybody here? Yeah, there he is, great. Okay. So, following Jensen et al. From the TFP, this is a nice way to eliminate data and case. So even our core language has still got too much. We still want things to be simpler. So let's get rid of data and case. How do we do that? Well, essentially, we do a sort of church encoding. So instead of the data structure D, where we introduce the constructors, if you like, capital C1, with various type arguments and so on, instead, each constructor becomes something which takes, think of these as the case alternatives. The function that would, I mean, why do you want this construction? Well, presumably because you're going to do something with it. Okay, why don't we install the continuation, even if you're going to print it? Okay, well, there's a printing routine is what you're going to do with it to turn it into a string. So the idea is we replace data constructors by these functions to which continuations are passed, and you select the appropriate continuation depending on which constructor is being represented. So this is the constructor Ci, so we select Wi as the continuation that's applied to the constructed components. So, simple example, even Booleans are handled this way, so false W1, W2 is W1, but true W1, W2 is W2. And to go with that, of course, we now know what to do when we come across a case. Okay, we don't have data constructors anymore, so the case doesn't make any sense. Instead, we turn it into this continuation passing form where what were the alternatives are now the bodies of the different continuations for the possible constructions that the result of E might have. And after doing that, we've now got some more lambda expressions, which we don't want, because they're complicated as well, so we lambda lift all over again. Okay, so at this point, our fact example looks like this, which is not too weird once you realise, okay, we're comparing it with one, this is the continuation for the true alternative, this is the continuation for the false alternative. Well, if we're going to make data weird, we wouldn't want primitive numbers to feel left out. So let's make numbers weird as well. At least we'll be consistent. So we'll have continuation passing style integers. Clearly music to somebody's ears. Oh, I did. Okay, so what's this all about? Well, we will choose to interpret integer values as if they are functions of type int arrow A, arrow A. So the function that is the meaning of 3, when applied to a function f, will give us what in the ordinary world would be f of 3. And then we will rewrite, just as when we change data, we needed to change case, we will rewrite primitive applications to fit in with this new, slightly strange view of the world, so that p and n, for instance, where p is a primitive, becomes n and p. Now you have to be a little smarter to be able still to read the definition of factorial, and I believe it is correct. Well, okay, but aside from the silly joke about wanting integers to be weird like all the other data, surely there must be some better reason than this for doing this. Well, yes, what this is all about is to guarantee that when we come to a primitive operation, its arguments will already be evaluated. So we don't need to worry about the case where they might not be. Finally, we reach the point where we could produce something you might stop with if this was a conventional interpreter and produce some kind of bytecode. Let's think of it as the code graphs. So each definition now becomes a triple. We want to know its arity. We want to know the number of nodes there are. We're going to represent the body as a graph. We want to know the number of nodes in the graph. Why do we want to know that? We want to know how much memory we're going to have to copy when this becomes a template. And finally, there's the body. And the body can be represented as a body graph in the following kind of little mini applicative graph language. Okay, so the interesting one is apps, which once again have their n-ary apps. So they are just lists of nodes again, where nodes are these things we're describing. So I won't drag you piece by piece through it. Take my word for it. This is a rendering into that form of the fact definition I gave you a moment ago. Here it is as a graph. Okay, then the bullets-like things are the apps. These boxes are where the argument is going to go. There is only one in this case. And so, okay, nothing to start with. Okay. Well, what have we got left then by the time we reduce to that level of code, and what does it mean? Well, it's time to give you the evaluation rules. This will only take 1.5 slides. Well, we can define evaluation by some kind of small step transition. We can describe, let's call them stack transitions. So stacks will just be sequences of nodes of the kind I've just described to you. We're going to start off with something like fun main. Of course, main won't literally be a string, and allow me notational liberty here. There will be some reference to a main definition somewhere, but we will start from the initial state there, and the final state will just be an int. So at the moment in the machine, the final result is an integer. Computation along the way may deal with what were data structures, functions, etc., but the final result at the moment is just an integer. And here are, since there are 5 kinds of nodes, we need 5 evaluation rules. So here we are, interpreting integers as weird functions in the way that we promised we would. So when we come across an integer at the head of the stack, what we do is we swap the top 2 stack elements. You may say, well, how is it, you're just deferring the problem. I mean, something sooner or later has to deal with integer in the ordinary, sensible way, otherwise the world would collapse. Well, the primitives know what to do. So here's primitive arithmetic. So if you have a primitive arithmetic operation at the top of the stack, it recognizes that these are ints, as in ints, like they usually are. And I will do my usual thing. So I will do AXY and replace the top of the stack with the int, which will then get swapped and so on. Okay, same with comparisons. Apply, we simply take the nodes from the application and we spray them onto the top of the stack. And then finally, here we are with a function, more generally it could be an arity 0 definition. Anyway, the definition of something called f. And we instantiate its body. And we instantiate its body with respect to, so B is the body drawn from F, and we instantiate it taking any arguments from the stack S. So here it is. This is the template instantiation bit. This is going to be the bottleneck that I referred to earlier. Okay, well that's all very well, but these are abstract rules. I mean, memory is entirely implicit. We seem to be quite a long way away from an FPGA. But if we go back for just one further slide to the representation I showed you before, we can take one further stage in the compilation. We can take these body graphs into bit vectors. The idea is this, that we finally code the bodies as sequences of 18-bit node descriptors. You remember 18 bits is the convenient length attached to those 1K memories. And the N-array applications now become n+1 contiguous node descriptors, 18-bit blocks. And there's essentially a marker bit. These are N-array applications, so how do we know when we come to the end, since it's just a stream of these bits? Well, there's a marker bit in each 18-bit block. 3 of the bits are used for tagging, and there's a marker bit that says, is that the last node in this app? And references to other apps are now simply offsets from the start of the body. Okay? So the code for fact looks like this. Okay? So these red blobs are full stops. That's the marker bit saying, and that's the last 18-bit chunk in this body. And here's an example of one of these application graphs. It says, well, actually you want application 4 at this point. That's the one starting here. So when we get down there on our FPGA, what do we want to do when we want an instance of the body of fact? We want to copy this block of memory. And in doing so, we want to substitute for the S references, so argument references have now become S for stack, from stack memory. And of course, we want to relocate these offsets into absolute offsets in heap memory. Does that make sense? You're not looking terribly happy with that. Yeah, no, it doesn't. Makes sense to some people. Okay, so I know you all want your tea. You all want your tea. Okay, so here we are on the FPGA, and the stuff that we've just seen gets put in here. There's a combinator memory. There's lots of it. 1K 18-bit words. Okay, and there is a heap, 32K 18-bit words, big heap. And Max has done curly stuff here. I mean, this heap is pipelined. You can get single clock cycle access to the heap. There's a stack, which is the stack I showed you in the evaluation rules. And there's another stack I haven't said anything about, which is a stack of application node addresses so that we can get shared update. And we really do get lazy evaluation, not just normal order reduction. And there's a stop and copy garbage collector, and therefore we need, it's a 2-space one, so there's also some GC space. And so there's 16K 18-bit words for that. And then of course there's all the stuff in the middle on the slices, which is the reduceron that does the reduction of the kind we just described. And the crucial point is that there are simultaneous reads and writes in these different memory units, so that we can, in a single clock cycle, do each 18-bit chunk or memory fetch. Okay. So, where am I? What's the time stop? Soon. I get the picture. Right. I have. Right. Let me encourage you. I have 2 slides and the conclusion. So, how is this done? Well, I do want to fit in things which cite other people's work. So, Kurt Gleison's Lava library, very nice, is used as the implementation vehicle for the reduceron. So the output is, in effect, a net list of FPGA components. There are now fancy libraries of things like Wired and so on, which goes right down to regarding each wire as a first-class citizen. But at the minute, things like placement and routing are just the Xilinx tools. So in terms of this Vertex 2 FPGA we're using, of the 56 block RAMs potentially available, current implementation uses 51 of them. The slices, however, well, something, a much smaller fraction of the total possible number of slices, so that could become significantly more complicated but still fit on this machine. And the theoretical, or in principle, maximum speed of this device with any circuit design on it would be 140 megahertz, where you never attain that. The actual speed attained for the current reduceron design is something like 96.5 megahertz. So, will you ever get your my PC goes faster on functional programming card? Well, not yet you won't, but we've got some early results. So we've got some preliminary performance results on small test programs. And the reason they're small test programs is quite simple. We've only got 18K bits to put the combinator code in. We could alter that. So we've got things like Fibonacci numbers, prime numbers, permutations, n-queens, strict arithmetic, puzzle solutions, and so on. So for these, the computation is done, but what's actually computed is the count of the number of solutions or something like that. So I mentioned that YHC is a quick bytecode interpreter for Haskell. So actually, this lines up with the SAPL technology that we've stolen. Actually already reduceron, if you simply write the reduceron type evaluator, again on a PC, it actually goes slightly faster than YHC. It has to be said it's stripped out. It's not carrying all the Haskell luggage that YHC is carrying. Even so. And on the FPGA, well, you may say, oh, you cheated. We want to see this. You know, the FPGA goes faster. You've just gratuitously thrown in 2 times here. Well, I'll come back to that in a moment. Yeah, so you're getting already better than half that speed on the FPGA. So, well, you're going out and sort of throwing yourself in the lake or something. I mean, you didn't do it. Well, hang on a minute. Don't forget that the clock frequency on the PC, well, I haven't told you, but the clock frequency on the PC is not much short of 3 gigahertz. The clock frequency on the FPGA is only 96 megahertz. So the clock speed is 30 times against us. So, but even so, what about this 2 times? Can we do anything to get rid of it? Well, then the conclusion slide, let me mention, the answer to that is yes. And even by the time we write the final version of this paper, we think we'll get another 3 to 4 times speed up, simply by widening the memory. I mentioned that you can cascade memory together. At the moment we've got this 18-bit wide memory, which means, yeah, you do it in one cycle, you do your 18-bit block of template instantiation. But of course, there's no reason in terms of data dependencies why, if the machine could do it, you shouldn't copy the entire supercombinator body in one go. So what we'll actually do is widen the memory out to, say, 72-bit chunks, and then we just get straight, more or less, linear speed up. So we get 3 to 4 times speed up, we reckon, by widening the memory. And for that matter, if we simply updated our FPGA to something a little more recent, well, then the clock speed there would go up by another factor of 3 as well. So, to close, so yeah, clearly we'd like to be able to run bigger applications. And yes, of course, we'd like to be able to outpace GHC on the PC. And then we start asking people like John, who's talking to me about this only this morning, saying he had exactly the same ambition to have your functional programs go faster going. Thank you.
Scale memory. They thought about how to combine this with a PC with a normal big memory so that you, because we're never going to be able to have comparable memory size on the FPGA.
Right. So John, for those people at the back who maybe didn't hear, the gist of John's question was, well, if you're going to be serious, you have to have a seriously large memory, otherwise you won't be able to do what you can do on the PC. We have not thought, as far as I know, Matt has not thought about any arrangement directly linking a PC memory with a FPGA memory. Something like that. The assumption that you work your functional program onto the FPGA board and you process the stuff. Of course, you can, I mentioned that this particular machine doesn't have one, and you can, no problem, 10 times that much memory with the machine. You may say, well, that's still not very much. But you can quite, not all, there's a difference between saying things are memory intensive and saying they need massive resonance. Don't confuse, we can confuse those 2 things. So something can be memory intensive in the sense that the beta reduction operation, for instance, is memory intensive. But it's not in itself necessarily consuming memory because things are garbage collected. So we'll wait to see how much we can do.
You can certainly get cards in the same family, which are chips in the same family, which have got 10 times as much memory.
Isn't the explicit substitution that you do still the main slowdown? Is it not happening that the substitution is still going on and other things have to wait?
No, because the access, you are substituting from the stack. And the access to, you can simultaneously access the stack, access the template, access the heap.
Yeah.
And for each chunk of the template at a time, and it's one cycle, you do all of those things in parallel, and do the address relocation.
Yeah, but you have some going through to make the substitution.
Going through each template, we can get linear speed up from that simply by widening the memory, by cascading memory blocks. So notice, in all of this, there is of course the further possibility beyond that, which is to actually do some parallel graph reduction in the usual sense of that term. But we haven't even begun on that. So in terms of, for instance, does this change semantic? No, it's a sequential lazy evaluator at that level. So the parallelism is within the reduction steps.
So maybe you answered my question, but it doesn't seem to be doing anything about the bottleneck.
Sorry, anything about
the memory bottleneck, the von Neumann bottleneck.
The question is, but I thought we were going to do something about the von Neumann bottleneck. Well, yes, we are, maybe at a different level from the one you expected. The point is there is a von Neumann bottleneck. If you think about template instantiation, think about doing graph reduction. Okay, we know we want to reduce this function application to an instance of its volume. That single operation, which is after all the major operation you're doing in the graph reduction implementation, just look at one of those operations. It is hampered by the von Neumann bottleneck. Because in doing that operation, all of a sudden you want to access several pieces of memory. And on a conventional PC with a single memory, they will all have to wait their turn to transact down von Neumann bottleneck. So what's happening here is that you are accessing the different pieces of memory concurrently, and the architecture of the machine is being exploited to allow everything to happen in one cycle. Does that make sense?
So it is a constant factor. You're basically just widening the buses. You're not like allowing an arbitrary number of memories to be used.
Okay, so the question is, well, there's still a fixed number of memories. That is true, although as I say, there's clearly then potential beyond that to look at things like speculative reduction and so on. But then you get into semantic difficulties. Yeah.
So, thank you very much.